For the remainder of our discussion for this week, we are going to talk about conservation of momentum, okay, and what we call an isolated system. An isolated system is defined by a system for which there are no external forces. No external forces. Take whatever system you want, draw a little box around it. There's going to be no external forces acting on that system. For such a system, we can say that the sum of all of the momentum remains constant at any time. And usually we think about conservation of momentum when we're thinking about a collision. Before the collision and after the collision, the momentum is always conserved. That means that the total momentum in the system remains unchanged. We can also think about conservation of momentum even without a collision, but the idea is that within any system that you can draw a box around, if we have no net external forces acting on the system, we can say that our momentum is always conserved. And remember that our momentum is the mass of our object times its velocity. Momentum is a vector, so that momentum vector is going to be pointing off in the same direction as our velocity vector. In this first problem we're going to solve, actually there's not a collision, but we can think about our whole system and think about the sum of the momentum before and after some action in order to figure out what are the velocities in our system. Okay, so we're going to have an archer here that's standing on frictionless ice, and our archer is going to fire a 0.5 kilogram arrow horizontally at 50 meters per second. The combined mass of the archer and the bow is 60 kilograms. What velocity does the archer move across the ice with after firing the arrow? Let's look at the knowns and unknowns in our problem to get started. We have an archer, which I'll call M1, and we see that the combined mass of the archer and the bow is 60 kilograms. So I'll just call M1 the mass of the archer plus the bow. That's 60 kilograms. M2 is the mass of our arrow, which is 0.5 kilograms, 500 grams. The initial velocity of both of these objects, V1 initial, are 0, because we're starting from rest for both of these objects. Okay, so their initial velocities are 0 in both cases. We are told that the archer fires the arrow horizontally at 50 meters per second. So that means that our arrow, after this event, which is the firing of the bow, our velocity of the arrow is 50 meters per second. So I'm going to call that V2 final. We need to find the final velocity of the archer. With what velocity does the archer move across the ice after firing the bow? So that's what I'm going to call V1 final, question mark. Okay, so to solve this problem, we're going to use conservation of momentum. That says that the sum of all the momentum in our system to begin with has to equal the sum of all of our momentum at some later time. So our momentum before the arrow is fired is M1 V1 initial plus M2 V2 initial, because momentum is mass times velocity, okay? And then that has to equal M1 V1 final plus M2 V2 final, okay? So we are starting from rest in both of these situations. So our initial momentum for both the arrow and the archer is 0. So 0 has to equal M1 V1 final plus M2 V2 final. So we need to solve this equation for V1 final. The velocity of the archer after firing the arrow, which we are calling V1 here, V1 final. So if we solve this equation for V1 final, I'm going to move this term, M2 V2 final, to the other side, minus M2 V2 final equals M1 V1 final. And we divide both sides by M1. V1 final equals minus M2 V2 final over M1. So I solved this equation, or I've solved this equation for the velocity of our archer after firing the arrow. We just need to plug in the values. So we've got minus the mass of the arrow. Remember, we called arrow 2. We called the archer plus the bow 1. So the mass of the arrow was 0.5 kilograms times the velocity of the arrow, 50 meters per second, divided by the mass of our archer plus the bow that he's holding, which is 60 kilograms. So if we do all that, we see that the units per kilograms cancel on top and bottom. We're going to be left with units of meters over a second. And our answer is equal to minus 0.417 meter per second. Okay, so after the archer fires the arrow, and he's on a frictionless surface on the ice, because we had conservation of momentum, the arrow is going to go forward, and that means that our archer is going to go backwards in space. It's going to go opposite the direction that the arrow was fired. The direct result of Newton's third law: for every action, there's an equal and opposite reaction. That example that we just went through did not involve a collision. Okay, we had two objects that were kind of sitting together, and then they went off in separate directions. Okay, but often when we think about conservation of momentum, we're thinking about collisions. And the remaining problems that we're going to work through here are going to be about collisions. A collision in which the colliding objects stick together and then move with a common final velocity are called perfectly inelastic collisions. A collision in which mechanical energy is conserved is called a perfectly elastic collision. The important thing to keep in mind with collisions is that momentum is always conserved. That means that the sum of all of your momentum before the collision equals the sum of all of your momentum after the collision. But that is not true always for mechanical energy. Mechanical energy is our kinetic energy and our potential energy. Okay, so in a perfectly elastic collision, your energy is also conserved before and after the collision. But if you have a perfectly inelastic collision, the energy is not conserved before and after the collision. So that means that if you have an inelastic collision, you're going to lose some mechanical energy. Okay? That energy is going to be converted into friction, sound, vibrations, like crunching up of the material, a bunch of other things, but we're not going to be able to conserve energy. So we're going to lose some energy in that process. But when we have elastic collisions, we conserve the energy. The sum of all of the energy before the collision equals the sum of all the energy after the collision. So we're going to work through a couple of examples of when we can use conservation of momentum and conservation of energy. This problem is a conservation of momentum problem, and it's also an inelastic collision. Okay, so we have two cars. Here we've got a truck with a mass of 1,800 kilograms that's traveling eastbound at 15 meters per second, while a car of 900 kilograms is traveling westbound at 15 meters per second. The cars are going to collide and become entangled and have a head-on collision. So we need to figure out what is the speed of these cars after their collision, V final, okay? Find the change in velocity for both cars, and find the change in kinetic energy of the system consisting of both cars. Okay, so in order to start this problem, well, first we have to remember that momentum is a vector. Okay, momentum is our mass times our velocity. The momentum vector points in the same direction as the velocity vector. Okay, so for this car that's traveling to the east, we'll call this car 1. It's got mass 1, initial velocity 1,
to the east, which we're going to say is to the right, is positive. Okay, and our second car, I'm going to call that car 2, mass 2. It has an initial velocity to the west. Okay, and so we're going to call west negative, along the negative x direction. So car 2's initial velocity is minus 15 meters per second. Using conservation of momentum, we're going to figure out what the final velocity is of this tangled car mess. After those two collide, they're essentially going to become one object, and then they're going to move with some final velocity. Okay, so if we do conservation of momentum for this problem, we've got m1 v1 initial plus m2 v2 initial equals m1 plus m2 v final. Okay, so m times v, that's the momentum. So we've got the initial momentum for our first car plus the initial momentum for our second car has to equal the momentum of our combined cars at the end, because they smush together, they become one object. And so the momentum at the end is going to be the sum of the masses of those two cars together, now they've merged to become one object, times their final velocity. Okay, so the momentum, they all are one object. We're going to put that final momentum by taking their masses together and multiplying it by v final. Okay, so we have to solve this equation for v final. We just divide both sides by m1 plus m2, and whenever we do that, we get v final equals m1 v1 initial plus m2 v2 initial over m1 plus m2 equals. Okay, so we've got our mass 1 was 1,800 kilograms times 15 meters per second plus m2 was 900 kilograms times minus 15 meters per second. Remember, velocity is a vector. It's going along the negative x direction here, so we put the minus 15 meters per second here for its velocity, and then we divide by the sum of their masses. So 1,800 kilograms plus 900 kilograms, and then that gives us a final velocity of 5 meters per second is v final. Okay, so they smush together, they end up still going forward after the collision at a speed of 5 meters per second. Okay, so then for part B, what was the change in velocity for both of these cars? So delta V for car 1, the change in velocity is always your final velocity minus your initial velocity. So for car 1, well, the final velocity is 5 meters per second because it's kind of smushed in together to the other car to become one object. So we've got 5 meters per second minus that car's initial velocity, 15 meters per second. So the change in velocity was minus 10 meters per second. Okay, so it slowed down. Okay, and then the change in velocity for car 2, it slowed down, but in the positive direction. Okay, and then for car 2, we've got v final minus v initial. It was initially, its final velocity is 5 meters per second combined with the other car moving forward. So 5 meters per second minus car 2's initial velocity, which was 15 meters per second, but in this direction. Okay, so then we have 5 meters per second minus negative 15 meters per second. Minus a negative becomes a positive. So the change in velocity for car 2 was 20 meters per second because it was originally going 15 meters per second in this direction, but after the collision, it ends up with a forward velocity of 5 meters per second. So subtracting them, the change in velocity was a total of 20 meters per second. All right, and then finally for part C, we need to find the change in the kinetic energy of the system consisting of both cars. So the change in kinetic energy is going to be the final kinetic energy of our system minus the initial kinetic energy of our system. Okay, So let's just start by finding the final kinetic energy of our system. So KE final is going to be 1/2 times the mass, which is the sum of those masses because it was an inelastic collision, times the final velocity squared. Okay, so that equals 1/2 times 1,800 kilograms plus 900 kilograms times the final velocity, which was 5 meters per second squared. And that gives us a kinetic energy of 3.375 times 10 to the 4 joules. Okay? Remember, kinetic energy has units of joules. And then our initial kinetic energy of our system is going to be the kinetic energy of car 1 plus the kinetic energy of car 2 before the collision. So that's going to be 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. Okay? And then that's equal to 1/2 times 1,800 kilograms times our initial velocity, 15 meters per second squared of our first car, plus 1/2 times the mass of the second car, 900 kilograms, times its initial velocity, which was minus 15 meters per second, but we're going to square that, so it's going to become positive, okay? So those become 3.038 times 10 to the 5 joules is the kinetic energy that we start with. So to find our change in kinetic energy, we have to take our 3.375 times 10 to the 4 joules and subtract it from our initial kinetic energy, 3.038 times 10 to the 5 joules, okay? And that difference is negative 2.7 times 10 to the 5 joules. The negative here because we lose energy. We lose energy in the system when we have an inelastic collision. So that means that our initial kinetic energy was bigger than our final kinetic energy. Some of that energy was lost through crumpling of the cars, through friction, through drag, etc. Okay, so that's how we will solve this problem right here. Now, you know, we want to know, like, okay, we have a quantity, 2.7 times 10 to the 5 joules, but what does that mean? So you can figure out what percentage of this change of energy that is compared to our initial kinetic energy. So if you take your change in kinetic energy, our 2.7 times 10 to the 5 joules, and divide it by our initial kinetic energy of the system, 3.038 times 10 to the 5 joules, that turns out to be 90%, or actually 89%. Okay. So we lose 89% of the initial kinetic energy during this collision.